Let's talk about extensions of the transportation problem. Of course, the transportation problem is a stylized model. There are some idealized assumptions. However, it is still useful for practical cases because it gives us a very nice starting point for extensions, for real-world extensions, for more complicated constraints or objective functions that we might want to consider. So let's have a look at some simple extensions, straightforward extensions of the transportation problem. The first extension I would like to discuss with you are infeasible routes. So let's jump back to Salma's fishery, to that example. Let me open the slides from the last lecture. Here we have transportation relations from the 3 factories to 4 different warehouses, and we have some unit costs given in this matrix, in this table, for each transportation relation. For example, from factory number 1 to warehouse C, the cost per kilometer are 380 base. Okay, now what we want to add to our model, and of course now every of these 12 3 times 4 transportation relations can be chosen by the solution of our model, by our solver, by our company. So all the transportation relations are feasible. But maybe Salma wants to say, I do not want to deliver from factory 2 to the Carrefour warehouse number C. Or I do not want to deliver from factory number 3 to the Matra fish market. Maybe she knows that there's a lot of traffic at the expected delivery time, and this will cause a lot of delays. However, this traffic is not part of our model. But Salma knows from other information, from other data outside the world of our model, that she wants to block, that she does not want to allow a transportation, say, from F3 to D or from F2 to C. So now, without changing the model in an extensive way, without including, for example, traffic requirements, how can she block these relations? We call these also infeasible routes. So she can just do this simply by increasing the cost of this relation. When she wants to block F3 to D, she can simply increase the unit cost on this relation so that it becomes very unattractive for the solver to choose this relation. So for example, if she puts unit costs of 10,000, 20,000 base per kilometer, then it is highly unlikely that this relation gets to be chosen. So by just increasing the unit cost on a relation, we can make it more unattractive, and if the unit costs are high enough, we can guarantee that this relation will never be chosen. So let's jump back to today's slides. So in our example, we want to block F2 to C and F3 to D. When we write it in our mathematical model, we say we want to induce prohibitive high cost on this relation, and instead of choosing an actual cost number, we write this as a parameter, and traditionally we use the letter big M for this relation. This means we need a number that is high enough so that it is blocked. Why do we write a letter M, a parameter, and not actual cost data? Well, maybe we want to use this model for completely different cases with 50 warehouses and 50 factories, or 10 factories and 200 warehouses with completely different cost data, and then it would be, we could not see that we want to block a route between a factory and a warehouse if we just write an actual number. Therefore, we write big M so that we can adjust this number always when we want to solve the model using actual data. Now here, for the actual data we have, we could use 300,000 baser as a proper value for M. This would guarantee us that the relation is not chosen. How did I decide on this 300,000? Well, this is approximately the solution, the minimum cost solution when I solve the data via the Excel solver. Other values might also work, but if it's too small, say you choose 1, it will no longer work. So please try this when you solve this via Excel. So now I put on the relation on the cost F2 to C and F3 to D. In this cost table, I put, instead of 1,730, I put 300,000. And then I solve the model in Excel again, and I get this updated solution. Please compare this solution with the previous solution where the transportation was allowed. Though there are some slight changes in the values because now one road is blocked. If we go back to the previous solution where the transportation was allowed on all the roads, you see that, for example, from F3 to D, 10 units were transported. Now in the new solution, this is 0 and the 10 units are distributed on other locations. Exactly what we want. Now, when we look at the objective function, when the transportation of all relations is allowed, the value was 299 reals and 80 baser. What is now the value of the new objective function? Particularly, is this value higher than the previous solution, the same, or is it lower? Think about it. What needs to be the outcome? You can answer this question without solving the model again. When we increase the parameters of the objective function, then the overall solution, the value of the objective function of the optimal solution, can only increase. So if we increase the cost parameters on the relations, then the value of the objective function, the total cost, can only increase. It's not possible that we find a better solution for lower cost. This is never possible. It might be possible that the value stays the same. For example, if we look at the relation F2 to C, we see in the original variant of the model there was no transportation amount between these two locations, F2 and F3. Now if we just increase this value from 1,440 to 300,000 without changing the other ones, then the value of the objective function will stay the same because we did not use this relation in the first place. But in general, it can only stay the same, the value of the objective function, or increase when we increase the cost parameters. And here, the value of the objective function is slightly increased. You see the impact is not very strong, but you can see the effect. And the interesting thing is now that we could make a change in our model. We could block individual routes, but there was no need to change the mathematical formulas of the model. There was no need to change the way the model was set up in Excel. The only thing we needed to change was the input data. Though by manipulating the input data, you can, at least to some degree, manipulate the working principle of the model.